usually define the light energy in terms of colors. And the reason, but typically what we say here is that people talk about the frequency of light. So in other words, the energy of light is closest to the frequency of light. And it's the frequency that people associate with the color of light. So here's what we know. Okay. So we're only going to deal with the visible spectrum, but I should say here that the electromagnetic spectrum, and spectrum is just a fancy word for what? The kinds of light. So the electromagnetic spectrum comes in 6 categories. And if we get all the way to light, I'll explain what these categories are. They come in 6 categories. But we will only focus on visible light. Like, for example, microwaves, right? We're not going to focus on microwaves because to describe the energy is too complicated. I mean, we can do it, but it's not worth our time. We're not going to talk about X-rays or ultraviolet lights or infrared lights. But what we will talk about is visible light. And this is the spectrum of visible light. Okay, this is the spectrum of visible light. So what's the most important thing? The most important thing here is what? The energy of light, the photon energy. And what you're seeing here is that look at the energy of the violet light versus the energy of the red light. And so you could see here is that this is low energy for red. Violet, on the other hand, is the high energy of the spectrum. Right? We can see that. And then you could see that somewhere in the middle right here, somewhere around here, you could see that this is sort of like the mid energy region. And this is for yellow, green. What's interesting about this thing here is that this is most light emitted by the sun is this color. That's what most of the light is coming from, is in this color. So what do we find? This is what you see best in, is in yellow green. So then if we rank the energies, what we're seeing here is that you could see that violet is going to be greater than blue, which will then be greater than green, which will then be greater than yellow, oops, as well as orange, which will be greater than red. There's all these colors. So once again, this is the high end. This guy is the low end of the spectrum. So now we can go back and look at what actually happens. So remember what we said here before. What we said here is that the size of the jump tells us the color of the emitted light, right? In other words, the size of jump is going to be proportional to the color emitted. So that's a statement that we can make. So here we go. Let's draw 4 energy levels here. So we go 1, 2, 3, 4. So then I'm going to get 4, 3, 2, 1. And we're always going to have an electron right in here. So this is the lowest possible state right here. So all electrons will eventually decay to that spot. Since I'm going to do this a couple of times, I'm going to copy this and just paste it. Okay, so let's look at this thing here. So check this out. Let's say I have an electron that's in the 4th energy level. What it does here is it's going to do what? It's going to decay. And as it decay, because that's a big jump, it has to emit higher energy light, which is violet in this case. So in this case, we say big jump. In this case, we're going from 4 to 1. Then it means so then you have high light energy. But let's say we have an electron like this, which then goes all the way down to here. Well, because this is sort of like a mid-sized jump for this atom, then it's going to emit green light. Or if I have an atom that's only right here, it's going to emit lower energy light, which is like red in this case. Right? So what we're seeing here is that this is a mid-sized jump as you go from 3 to 1. So therefore, you get mid-light energy. And this one is a small jump. In this case, you're just going from 2 to 1. So therefore, this implies that this is the lowest energy of light. And so here's the thing about this thing. So why is quantum mechanics so special? Because now when we have electrons and atoms and they're jumping, here's what happens. The emitted light of jumping electrons are observed in atomic spectra. And this is the biggest proof of why quantum mechanics is so strong. So it looks something like this here. So let's say that we have an atom. Okay, I think I still have this, so let me put this here. Let's say that this is our atom right here. So if you look at this atom, here's what we're going to see here. I have this atom, and this atom is going to jump all the way down, and it's going to emit violet, of course. Then I have this atom, and this atom, excuse me, this electron is going to jump all the way down. So what's it going to do? It's going to emit that green light. And if I look at this guy, and it jumps down, then we know it has to emit the red light like this. So atomic spectra is a collection of lines of color. And what you're seeing here is that for each color emitted, you get a line. So look at the spacings here. So what you're seeing here is that I get a light for the violet light, I get a line for the green light, and I get a line for the red light. And what's important here is that note, because the energy levels have equal spacings, the spectral lines are also equal spacings, which is kind of wild. So here's another one. We talked about this earlier. It turns out that hydrogen has a unique atomic spectra. So if you look at hydrogen, it looks like this. So you go 1, 2, 3, 4. So you're seeing here is that this is 1, 2, 3, 4. So when you look at the spectra, so this would be sort of like the hydrogen spectral lines. This is what you would see here. You would see in this case that you get the violet line, but look how the third one is closer. So then it would look like this. And then when you look at 2, then to 1, you're going to see that the spacing then looks something like that. So you could see that the spacings are different. So here you have different spacings of energy levels. So therefore, you get different spacings of spectral lines. But this model is too simple. But this explanation is not complete. Oops. And what we find here is that we don't show all the spectral lines. So what do I mean by that? Well, let's go look at this atom again. And what we're really doing here is that we went back up here, if I can do this very briefly, and look at this process right here. So if I was to bring this down here, and let me just move this over here, and let me sort of like bring this picture here. What are we actually seeing here? And what you're seeing here is that you're seeing this, that when electrons jump, they can take different paths, right? We're saying that electron paths can make multiple paths. So what do I mean by this now? So check this out. What I'm going to do here is that I think I'm going to extend these lines a little bit. Let's look at the purple one. If I look at that purple atom or the purple electron, I don't know why I keep saying purple. So note that this has 3 possible jumps, right? So we could go 1, 2, 3, right? So this is going to be 1, 2, 3. So it has 3 possible jumps. Now let's look at the green one. The green one has 2 possible jumps. It could jump to here, or it could jump all the way down to there. And so in this case, this is 3. So then this is 4, 5. And then if I look at the red, well, the red only has 1 possible jump, and this will make it 6. So what you're seeing here is that because the number of jumps, so what we're seeing here is that the total number of spectral lines is equal to all possible jumps. So if I look at this, it's not 3 lines, but what you're seeing here is that, look at that, because the energy spacings are all the same, it's going to look something like this here. So I'm going to get 1, 2, 3. Then I look at 2 of the green, and then 1 of the red. And this guy's here is going to be what? This is 1, 2, 3, 4, 5, 6. So this atom has 6 spectral lines because there are 6 jumps. Okay, so if I look at my little flow chart here, we see that we have unique structure. Of atoms. Now, I got to be careful here, right? When I say unique structure, maybe I shouldn't say unique structure. Maybe unique electron structure, right? We have unique electron structure in atoms. So if I have unique electron structure, then that means I have unique electron jumps. But if I have unique electron jumps, then that means I have unique spectral lines. So as a consequence, this is why the spectral lines are called the fingerprints of atoms. So this is my little flow chart to just guide you to thinking that this is the reason why spectral lines are so important. So what I'll do here is that I'll show you, what do I mean by this? So these are actual spectral lines. Actually, they're colorized, but look at hydrogen. So if you look at hydrogen, look what you're seeing right here. This is hydrogen. Look at the structure here. Okay, look at the structure. And if you're looking at the structure, you could see by looking at the spectral lines, you could come back and you could say, oh, I see that the spectral lines are looking something like this. Right? They're getting smaller and smaller and smaller. So if you look at this, this must be the first excited state when it jumps to the ground state. Then this guy has to be 3 and 2. And then you could see here is that this is 4, 5, 6, 7. So there are 7 jumps in the visible spectrum. And look at sodium. Sodium is a complicated molecule, right? Because when you look at sodium, you're seeing that in the visible spectrum, you're only getting 3 lines. And if you try to get the structure of that, you're going to go like, wow, I have no idea what's going on. So what that really means here is that there's emitted light in the infrared and the UV region. So you can't get the structure from the lines until you look at other parts of the spectrum.